Hi there, welcome to lesson 4 of the course. Today we're talking about Charles Lyell and Lord Kelvin and their attempts at finding an ultimate age of the Earth. Now I mention Lyell because he's one of the fathers of modern geology. If it wasn't Hutton, we'd say it's Lyell. And the reason is he was a professor of geology at King's College in London around 1830 and on. He had adopted Hutton's idea of gradual change, uniformitarianism, as he called it. This idea that the Earth is changing very gradually and in processes that are still in action today. Now, I don't want to get the wrong idea across here that Hutton and Lyell were these shrewd scientists trying to batter down the tradition of religion and religious belief onto how the Earth was created. They were devout Christians, and it was actually quite difficult for them to reconcile what they were observing in nature with the religious studies and that tradition. It would have been much more comfortable for Lyell to adopt the belief of catastrophism, which is the idea that a number of short, catastrophic events created the Earth as we perceive it today. This is sort of a thinly veiled justification, I suppose, of the biblical flood. That would be considered a catastrophic event that shaped the Earth. Now Lyell, although I'm sure it was difficult for him in the day, his scientific mind was strong enough that he couldn't accept catastrophism as a solution. He thought it was a return to speculation characteristic of older traditions. I'm pretty impressed by that because it would have been, it's easy to say that now, but we live in a different religious climate than they did. An interesting progression from Lyell's gradualism, his uniformitarianism, is that it inspired a young Charles Darwin to see that perhaps, like in geology, perhaps in biology, these gradual changes may lead not just rock formations, but species to develop and change very gradually over time. Lyell was not a fan of Darwin's theory of evolution, or rather theory of natural selection in evolution, because it had been pretty much observed and categorized that evolution had occurred. It was part of the fossil record. How that had happened was up for debate. Darwin said it was natural selection. Lyell thought perhaps it was more of a theistic, divine guidance. By the end of his life, Lyell, in The Antiquity of Man, had started to understand that he couldn't deny this any longer. And so it's kind of an impressive thing that even though he was a very religious man, his belief in observing the world around him and only coming to conclusions based on evidence led him to, although reluctantly, favor the idea of evolution and uniformitarianism. So we have Charles Lyell, whose ideology can be summarized in the saying, "The present is the key to the past." We have Darwin, who believed that over immeasurable amounts of time, natural selection caused evolution of species. And both of these theories require enormous amounts of time, perhaps infinite. One person, William Thomson, later to be known as Lord Kelvin, was not so sure that the Earth could be immeasurably old. His accomplishments, which are many, the most well-known are to do with heat and studying heat as a physical property. He's really well known now for having the heat scale of Kelvin, which, unlike other scales, begins at absolute zero, which, unsurprisingly, was a construction of his. Kelvin, based on what he'd seen of heat and the Earth and heat of the sun, believed that the Earth must be in fact cooling down. That seemed to be a property of nature that he was observing, that ultimately the universe cools. This got him onto volcanoes and the molten nature of Earth's subsurface, I guess you'd say. He knew that, and people had known for a long time, that volcanoes erupt molten rock, very hot rock. And he knew also that there's a geothermal gradient. All that means is that if you go very deep in a mine, it gets hotter. So the Earth seems to get hotter towards the center. Now he thought that perhaps at one time the Earth was entirely molten, a complete ball of molten rock. Given that, and we know at this stage, this is the late 1800s, 1860s to 1890s, Kelvin had worked out how long things take to cool. We know how big the Earth is. Eratosthenes figured that out thousands of years ago. And we know, well, he tested how long rock takes to cool. And it was a little bit hand-wavy in his calculations, but the premise was good. And he figured out, based on the idea that the Earth is steadily cooling, that the Earth can be no more than about 40 million years old, which actually doesn't seem like that long when we look at vast tracts of strata, the size of the world, and the number of these processes, unconformities. All these things taken into account, 40 million years is a pretty short order for all that to happen. But Kelvin was convinced. The main driving force of his ideology was the idea of heat death. And even in 1897, he was still convinced of this. Just think, that's less than 100... So here we are in 1897, less than 120 years ago, and Kelvin places the age of the Earth at no more than 40 million years. That's something to think about, because now we know the Earth is much older. But this is only 120 years ago. So where did Kelvin go wrong? Well, he assumed, for one, that the Earth was cooling at a steady rate, that no new heat was being added, that we started with a molten Earth, and it slowly cooled to what we see today. Now, it's a little unfair. It was actually a very good attempt by him to date the Earth. What he didn't know was that radioactive decay is actually heating the Earth, in part, from the inside out. So that immediately means that the Earth must be much older than Kelvin's 20 million years. How much older is the subject for another lecture, but what we can take from this is that science is advancing, and radioactivity is the key to further understanding. But what radioactivity is needs to be a whole other lecture on its own, and that's what we'll talk about next. And to do that, we'll have to look into what matter itself even is. And we'll go over that in the next lecture.